So welcome to class number 22 of basic electronics. So we are studying the voltage divider biasing scheme. So let me draw this voltage divider network over here. So this VCC is connected to the collector through this resistor RC. Then at the emitter we might provide a resistor RE. Of course this RE need not be present, but as I said earlier that this RE is put here to actually enhance biasing stability against any variation in beta. Okay, so we'll show this later. Right now just concentrate on this circuit. So this is our voltage divider biasing, and as I stated earlier that the AC voltage is actually put through this capacitor Ci over here like this, but this AC voltage is not a part of the biasing network, and right now we are actually interested in how the circuit is biased, or what are the biasing current and biasing voltage, or what is the operating point basically. Okay, and since this capacitor Ci basically blocks any DC current from flowing through it, this part of the circuit is not a part of the DC current flow, or this part is not required for DC analysis of the operating point. Okay, so right now we are just removing this part of the circuit, and we also stated the last day that this part of the circuit is also not a part of the biasing circuit. Okay, these resistors R1, R2, RC and RE are basically the part of the biasing circuit. Okay, so we will remove these parts from here. Okay, so now we are interested in knowing what is the DC base current that flows through the circuit, because the emitter current and the collector current basically depends on the base current. So to find out the DC value of the emitter current, and to find out the DC value of the collector current, and also to find out the DC value of the collector to emitter voltage, we basically need this current IB. Okay, because IC is actually related to IB through this equation IC equal to beta times IB, and IE, the emitter current, is also related to the base current through the equation beta plus 1 times IB. So to find out the DC values of the collector current and the DC values of the emitter current, and also to find out the DC values of VCE, we first need to find the DC value of the base current. Okay, now this circuit is actually quite complicated to solve, because the current flows through this resistor R1, and then a part of the current flows through the base as the base current, and another part of the current flows through the resistor R2 as the current through R2, and then this base current that enters and the current that comes out of the emitter are basically not the same. So this network is actually somewhat complicated to solve. It's not too much complicated, but it is some complication is there. It can be solved by some rigorous solution of equations, but it is actually much easier to solve this circuit if we use Thevenin's theorem. So let me just repeat that right now we are interested in the DC value of the base current, or we are interested in knowing what is the current that flows through the base. Okay, so remember that when we talked about the load resistor RL in case of Thevenin's theorem, we were interested in the load current IL. So right now we are interested in the base current, and since we are interested in the base current, this part of the circuit basically becomes our load. Okay, the base current flows into the base of the transistor, so this part of the circuit basically becomes our load. Okay. Now this base current is basically flowing into the base of the transistor. So let us simplify our circuit. The first thing that I would like to point out is because this part of the circuit is our load, because this part of the circuit is the load, therefore we need to find Thevenin's equivalent network between these 2 points. So between this point here A and this point here B. So we need to find out Thevenin's equivalent network between the points A and B. Okay. Now let us make some assumption that makes the circuit simpler. First of all, note that if I increase the collector voltage here, okay, so this is our collector terminal, and if I increase the collector voltage, the base current would basically not change. So no matter how much collector voltage I increase, the base current is not going to change. We already know that an increase in collector voltage does not increase the base current or the collector current or the emitter current if the transistor is operating in the forward active mode. So an increase in the collector voltage does not change the base current. This basically means that it appears as if the collector and the base are basically electrically isolated. Let us say that I have two terminals. So I have a terminal A and a terminal B, and terminal B is basically let us say connected to the ground, okay, or connected to the ground through another voltage source and a resistor, and then this is connected to the ground. Okay, don't confuse this A and B with the AB points here. Okay, so to avoid confusion, let us call this point X and Y. So now let us assume that some current is flowing this through these resistors R1 and R2, or Rx and Ry, let us say. So some current is flowing through these resistors Rx and Ry. Now I increase. Now let us say that we have an impedance Z between X and Y. Now let us say I increase the voltage at point X. So if this impedance Z is finite, then I would expect the current through Rx or Ry to change. I repeat again that here I have applied this voltage Vx, and now if this impedance Z that connects the points X and Y, if this impedance Z is finite, then when I increase Vx, the current through this resistor Rx or the current through this resistor Ry should basically change. Okay, if there is no current change across this resistance Rx and this resistance Ry, when I increase Vx, this basically means that this impedance Z is infinite, or in other words, this point X and Y are basically electrically isolated. There is no electrical connection between the points X and Y if on increasing the voltage at this point X over here, there is no current change in this resistor Rx and this resistor Ry. Okay, so note the behavior is similar here. If we increase this collector voltage Vc over here, then the base current is not going to change. Neither the emitter current is going to change. This means that the base of the transistor and the collector of the transistor are electrically isolated as far as the electrical behavior of the circuit is concerned. Okay, so just like we have concluded that if there is an impedance Z over here, and if on increasing this voltage Vx there is no current change across Rx or across Ry, then we can say that this impedance Z is infinity, or these points X and Y are basically open circuited, they are electrically not connected. So in a similar way, when I am increasing this voltage Vc and there is no current change across the base, then I can conclude that the base and the collector are electrically isolated as far as the behavior of the circuit is concerned, or there is infinite resistance between the base and the collector. So between the base and the collector, I can replace by infinite resistance here. Okay, so let me delete this base and the collector here, and let me replace it by an infinite resistance. So I deleted a large part of the circuit. So let me just delete this base to collector junction. So we have deleted this base to collector junction and replaced it with some resistor R0, where R0 basically has infinite magnitude, or the value of the resistance R0 is infinity. Okay, and we have to find, just as I stated, the equivalent Thevenin's network between this point A and this point B over here. Okay, so we have two quantities for Thevenin's equivalent network. One is the Thevenin's voltage VTH and one is the Thevenin's equivalent resistance RTH, and we have to find these two parameters. Now, how do we find Thevenin's equivalent voltage VTH? We just disconnect the load. So we disconnect the load from here, we disconnect this RE, and we disconnect this base to emitter junction also. Again, I deleted a large portion of the circuit. Okay, so I disconnected the load from here, and I basically have to find the open circuited voltage between this point A and this point B. Okay, so I have to find the open circuited voltage, and this open circuited voltage is basically my Thevenin's voltage VTH. Okay, now what is the open circuited voltage between these 2 points? Note that because this R0 is basically infinite, we can actually disconnect R0 from this circuit, or we can make R0 open circuited, because an infinite resistance basically behaves as an open circuit. So we can actually disconnect this entire part consisting of RC and R0, because no current actually flows through RC, since R0 is basically infinite. Okay, or in other words, let me reframe the statement. R0 is actually infinite, so this part of the network consisting of RC and R0 do not get to take part in deciding this open circuited voltage VTH. So we can actually disconnect this part of the network, because R0 is basically infinite. So we are just disconnecting this resistor RC from here. Okay, so now we can easily find this open circuited voltage between the points A and the points B. This open circuited voltage VTH is basically equal to R2 divided by R1 plus R2 into VCC. Okay, now what is RTH? So to find RTH, we basically have to remove the voltage source and short circuit that point. So to short circuit that point basically means that we connect this point to the ground. Okay, so if you do not understand why short circuiting it means ground connection, so let me actually show you how this voltage source VCC is actually connected. We just write VCC at this point here, but how it is connected is basically like this. So we have this voltage source VCC, which is actually connected to the ground. So we have this voltage source VCC over here, and so if we remove this voltage source, this basically, and replace this by a short circuit, this basically means connecting this point over here to the ground. Okay, so we are basically doing that, we are connecting this point to the ground. So let me just connect it to the ground. We have connected this point to the ground, and now we have to find RTH, we have to look into these 2 points, point A and point B, and find out the equivalent resistance. So we look inside this network and find out the equivalent resistance. Note that this resistor R2 here is basically connected between this point A and the ground. This point B is actually the ground point. So this resistor R2 is basically connected between this point A here and the ground, and this resistor R2 is also connected between the point A and ground. So R1 and R2 are basically in parallel. Okay, so RTH is basically the parallel combination of R1 and R2, which gives me R1 R2 divided by R1 plus R2. So we have found out Thevenin's voltage VTH and Thevenin's resistance RTH. Now, how does my equivalent circuit look? So note that nothing is changed at the collector end because we just wanted to find out the base current. Okay, so nothing has changed at the collector end. So we have RC over here, we have this transistor, and we have this emitter resistor RE. This point is VCC, and this was basically our load. Okay, this was our load, and we replace everything that is connected to the base. So this point was basically connected to the base, and this point was basically connected to the ground. So we replace everything that is connected between the base and the ground by the voltage source VTH and the resistor RTH. Okay, I repeat again that we are basically finding the Thevenin's equivalent network between this point A here and this point B here. So we are basically replacing everything that is connected to the point A, or we are replacing everything that is connected between the point A and ground by Thevenin's equivalent voltage and Thevenin's equivalent resistance. So this was the point A over here, and this is the ground. So the ground is the point B, so this is point B. So the load is this portion. So everything else that is connected between point A and point B is basically replaced by Thevenin's equivalent voltage source and Thevenin's equivalent resistor. So we have this resistor RTH, and we have this Thevenin's voltage source VTH, which is basically connected to the ground. Okay, so everything between point A and point B, everything that was connected between point A and point B excepting the load is basically replaced by Thevenin's equivalent resistance RTH and Thevenin's equivalent voltage VTH. Okay, so now the network is much simpler, and this network right now looks like a fixed biasing network. It is not exactly a fixed biasing network because fixed biasing scheme or fixed biasing network basically derives the voltage or takes the voltage from this point at VCC. Okay, but here we have a separate voltage source, actually VT. So this is not exactly a fixed bias network, but we can actually solve for IB as if we are solving for the IB for a fixed biasing network. Okay, so let us just see how. So we have this resistor RC over here, which is connected to this point VCC, and then we have this transistor, and then we have this emitter resistor over here, RE, and then we have this Thevenin's equivalent resistor RTH, and we have this Thevenin's equivalent voltage VTH, which is basically connected to the ground. Okay, so this was basically our configuration. Okay, now this network, after we have simplified it with Thevenin's theorem, is not really difficult to solve. So we have the base current that is flowing into the base of the transistor, and what we wanted to do, or why we actually simplified this network, was actually to find this base current. Okay, so how to find this base current? So we will basically apply Kirchhoff's voltage law in this loop, starting from this voltage source VTH, then through the resistor RTH, then through the this base to emitter junction, and then through this resistor RE. Okay, so we will basically apply Kirchhoff's voltage law in this loop. Now, so we write the Kirchhoff's voltage equation. VTH is basically equal to RTH times IB, because if the base current basically flows through this resistor RTH over here. So IB into RTH plus the voltage drop at the base to emitter junction. So this voltage drop over here. Okay. So the voltage drop across the base to emitter junction is approximately VBE on, provided that the transistor is in a forward conducting state. Then the voltage drop across this resistor RE. Okay. Now note that actually a current of magnitude IE is basically flowing through this resistor RE, and IE is basically equal to beta plus 1 times IB. Okay. So plus IE RE. So this is equal to IB into RTH plus VBE on plus IE is basically beta plus 1 IB times RE. Okay, so IB is basically given by VTH minus VBE on divided by RTH plus beta plus 1 RE. So the collector current IC is basically given by beta into VTH minus VBE on divided by RTH plus beta plus 1 RE. Now I told earlier that this resistor RE is actually used to enhance the biasing stability. Okay, so it is used basically to prevent the transistor collector current IC or the DC value of the collector current IC from varying when beta of the transistor basically changes. Now beta of a transistor or the common emitter current gain can actually vary due to temperature or due to aging of transistor or other factors, like if there is excessive heat dissipation and if the transistor heats up too much during the operation, then actually the transistor beta would actually permanently change. Okay, so these are basically various factors in which beta can vary, and if beta varies, then the collector current also tends to increase. Okay, and if the collector current increases, then the voltage drop across this RC would increase, and the voltage drop RE would also increase, because an increase in collector current also means the increase in emitter current. So basically this VCE would change. VCE would basically change. So we do not really want that, because as I said, the combination of the DC values of the collector current and VCE is known as the operating point or the Q point of the transistor, and typically we always try to keep this operating point at the middle of the forward active regime or at the middle of the load line. So we typically do not want this DC operating point or the Q point to actually drift away. Okay, so now here let us show that the collector current is almost independent of beta. If we can show that the collector current is almost independent of beta, then we can actually say that the collector current is immune against any variation in beta. Okay, now we know that typically beta is very large, and for good transistor beta can be of the order of 10,000 or something like that. For good transistors, beta is actually greater than 10,000. Okay, or of the order of 10,000, let us say. Okay, so in that case, if beta is of the order of 10,000, then this means that beta plus 1 RE should actually be much greater than RTH. Okay, so if beta plus 1 RE is actually much greater than RTH, then IC, the collector current, is approximately equal to beta times VTH minus VBE on divided by beta plus 1 RE. So this is equal to beta divided by beta plus 1 VTH minus VBE on divided by RTH. Okay, now if beta is of the order of 10,000 or something like that, then beta divided by beta plus 1 is approximately 1. Okay, so this is approximately equal in that case to VTH minus VBE on divided by sorry, this is not RTH but this is RE actually, divided by RE. Okay, since beta plus 1 is approximately equal to beta. Okay, so we have shown that the expression for this collector current for good transistors where beta is of the order of 10,000 or something like that, okay, in those cases the collector current is actually independent of beta. So the collector current does not vary with any variation in beta. Okay, so that is what I meant when I said that this resistor Re is actually used to enhance biasing stability of the transistor, or it is used to prevent the Q point or the operating point from drifting away when beta of the transistor varies due to temperature or aging of the transistor. Okay, so I hope it is clear to you all. Now let us actually do a small problem from voltage divider biasing scheme. We have already done a small problem on fixed biasing scheme earlier, so I am not repeating problems on fixed biasing scheme again. So let us do a small problem on the voltage divider biasing scheme. So we have this transistor here, this is RC, this is RE, and then we have this resistor R1 and R2. And you are given with the information that VCC is equal to 18 volts, R1 is equal to 33 kilo ohms, R2 is equal to 10 kilo ohms, RC is equal to 2.2 kilo ohms, and RE is equal to 1 kilo ohm, and beta is basically equal to 50. And you are basically asked to find out the base current. So this is the information that is given, and you are basically asked to find out the base current, the collector current, and VCE. Okay, so when I say the base current, the collector current, and VCE, this basically means the DC values of the base current, the DC values of the collector current, and the DC values of VCE. Okay, because there is no AC voltage in this model, so you are asked to find out the DC values only, or you are asked to find out the biasing values of IC, IB, and VCE. Okay, so we know that we have just learned that this circuit over here can actually be replaced by a Thevenin's equivalent network, where this we have this voltage source, we have this resistor RC and this voltage source VCC, and then we have this transistor, then this resistor RE over here, and this resistor RB, sorry, this resistor RTH, and this voltage source VTH. This we have already seen that this network on the top is equivalent to this circuit at the bottom. Okay, and we have also found out how to find out the values of VTH and RTH. So our VTH is basically R2 divided by R1 plus R2 into VCC. So this basically becomes 10 divided by 43 into 18 volts, and this is basically equal to 4.186 volts. So 4.186 volts. Okay. Similarly, RTH also we have seen the formula in the previous page. This is basically equal to R1 parallel to R2. So this is basically 33 kilo ohms parallel to 10 kilo ohms, and this is basically equal to 7.67 kilo ohms. So we have found out the values of VTH and RTH. Okay, now we need to calculate the base current. So again, as before, we basically use Kirchhoff's voltage law in this loop, starting from ground, then through this resistor RTH, then through the base to emitter junction, and then through this resistor RE. So note that the base current IB actually flows through this resistor RTH, but the emitter current actually flows through this resistor RE. Okay, so let us write this equation of the Kirchhoff's voltage law. So VTH is basically equal to RTH into IB, because the base current basically flows through this resistor RTH, plus VBE on, which is basically equal to or approximately equal to the base to emitter voltage when the diode is in a forward conducting state, or when the base to emitter junction is in a forward conducting state, plus the voltage drop across this resistor RE over here. So since the current of magnitude IE actually flows through RE, this should be IE times RE. Okay, so VTH is basically 4.186 volts, RTH is 7.67 kilo ohms, plus VBE on we are assuming to be 0.7 volts, plus IE is basically beta plus 1 times IB. So beta plus 1 is 51 times IB, into RE is basically 1 kilo, that's written over here. So into 1 kilo, so I am writing it as 1. Okay, so so IB times 7.67 plus 51 is equal to 4.186 minus 0.7 divided by no, not divided by, this is just 4.186 minus 0.7. Okay, so IB is basically equal to 3.486 divided by 58.67, and the answer is in milliamps because the resistors were in kilo ohms. So this is equal to 0.0594 milliamperes. Okay, so we have found out the value of IB. Now the collector current IC is basically equal to beta times IB. So beta times IB, so this is equal to 50, beta is basically 50 into 0.0594 milliamperes, and this is equal to 2.97 milliamperes. Okay, and so we have found out the values of IB and IC. So VCE is basically equal to VCC minus the voltage drop across the resistor RC, so minus ICRC, minus the voltage drop across the resistor RE, so minus IERE. So if you do not understand, let me take you back to this figure over here. So this voltage drop across the collector to emitter junction, this VCE, is basically equal to this VCC minus this voltage drop across this resistor RC, which is IC times RC, minus the voltage drop across this resistor RE, which is IE times RE. Okay, so 18 volts, this is equal to 18 volts minus IC RC. IC is 2.97 milliamperes. So 2.97 milliamperes into RC was basically 2.2 kilo ohms. So 2.2 minus IE is also approximately 2.97 milliamperes. Okay, because beta is equal to 50, so IC must be approximately equal to the emitter current. So IE is also approximately equal to 2.97 milliamperes into RE is basically 1 kilo, so into 1. So 18 volts minus 2.97 into 3.2. So let me check this value over here. So 18 minus 2.97 into 3.2 is basically 8.496. So 8.496 volts over here. So we have found out the values of VCE. So this problem is not difficult, as you can understand. It's not much difficult to solve. So this kind of problems you can actually expect in the examination. So we have discussed the two biasing schemes of the transistor, and next we will actually go to the AC model. And exactly why we discussed this biasing scheme of this transistor before going to the small signal or AC model of the transistor is because we will see that the parameters of the AC model of this transistor depends on the DC biasing currents or the DC biasing voltages, not voltages but DC biasing current mainly. Okay, so because the small signal parameters of this circuit depends on the DC biasing current, so a DC analysis or finding out the DC values of the base and the collector current are important before we can actually move to the AC model of the transistor. Okay, so let me write it here. Small signal or AC model. So RC, VCC, and then this point is actually grounded. Okay, and we do with fixed biasing scheme. So we could have also done with voltage biasing scheme. So there is voltage divider biasing scheme. There is not much difference, but right now we are showing this fixed biasing scheme over here. This is our base resistor RB, and just as before, the AC voltage is actually provided through this different path, where this capacitor Ci is actually present to prevent DC current flow into the AC voltage source. So this is basically the source resistance Rs, and this Rs is basically not a resistor which we have connected externally, but Rs is basically the source resistance of this voltage source VAC. Okay, so together this VAC voltage source and this source resistance Rs constitute this non-ideal voltage source. Okay, so Rs is basically embedded within this voltage source VAC. For example, those of you who are actually in electronics and telecommunication domain or in electrical domain, they would actually learn in the second or third year that this antenna also has a resistance of its own. So for an antenna, this Rs is basically its self resistance. Okay, so let us not discuss too much about these things, because our intention is actually to find out the small signal or AC model. And just as I stated before, that this is my AC current path, into the base. So AC current, and this is basically my DC current path into the base. Okay. Now we have already discussed that this base to emitter junction is basically a diode. Okay. So IE, the emitter current, is basically given by IE is approximately equal to IS exponential VBE divided by VT. Okay. So the base current IB is basically equal to IE divided by beta plus 1. So this is equal to IS divided by beta plus 1 exponential VBE divided by VT. Okay. Now this IS divided by beta plus 1, this we will write as ISB. So ISB exponential VBE divided by VT. So the base current basically increases exponentially with the base to emitter voltage. Okay, so let us draw this graph of base current against the base to emitter voltage. So this x axis or the horizontal axis over here is VBE, and this y axis over here is basically our base current IB, and this actually increases exponentially with VBE. So this is basically the graph of our base current versus base to emitter voltage. Now let us assume that the DC biasing has actually put the DC operating point at the base to emitter junction here. Okay, so there is this DC current path, and through this DC current path the DC current flows into the base of the transistor, and therefore a DC base to emitter voltage also develops. So let us assume that this point over here gives me the combination of the DC values of the base current and the DC values of the base to emitter voltage. Okay, so this point is this is basically the operating point of the base to emitter junction. Earlier we have discussed about the operating point of the collector to emitter junction, that is the combination of the collector to emitter voltage and the collector current. Here we are talking about the DC operating point for the base to emitter junction, that is the combination of the DC base current and the DC base to emitter voltage. Okay, so this point is basically VBE DC, or the DC base to emitter voltage, and if I extend this line in the horizontal direction, I would get the DC value of the base current. So I get the DC value of the base current. Now what does this AC voltage source here do? Okay, so this AC voltage source basically changes the total voltage at the base to emitter junction beyond VBE. So this AC voltage source can either increase the base to emitter voltage slightly, or it may also decrease the base to emitter voltage slightly. Okay, so this was our earlier point, or this is our DC point of the base to emitter voltage. Now because the AC voltage source is operating, or the AC voltage source is superimposing on the top of the DC voltage, so let us assume that the base to emitter voltage is basically increased by a very small amount, say delta VBE. Okay, so this voltage, this small increase in voltage due to the AC voltage source is basically denoted by delta VBE. So I repeat again that this point is the DC base to emitter voltage, and then because the AC voltage source is actually superimposing on the top of this DC voltage, the function of the AC voltage source is to slightly change this base to emitter voltage. Okay, because the base current actually depends on this base to emitter voltage. So when this AC voltage source increases or decreases the base current, the base to emitter voltage also changes very slightly. Okay, so this AC voltage source, let us assume that this AC voltage source increases the base to emitter voltage beyond the DC voltage by a very small amount, delta VBE. So the base current would also change. So the increase in base current is basically given by this amount. So I am extending this point in the horizontal direction. So this is basically the increase in base current. This is known as delta IB. So what is important as far as the AC model is concerned is how the AC base current is increasing with the AC base voltage. Okay, or how the increase in base current due to the AC voltage is actually related to the increase in the base to emitter voltage. Okay, so this relation between the small increase in the base to emitter voltage due to the AC voltage source and the small increase in the base current again due to the AC voltage source, okay, is actually important. Okay, so this slope of the IB versus VBE curve at this region is basically important. So this slope basically relates delta VBE to delta IB. So delta IB divided by delta VBE is equal to the slope of the IV characteristics of the base at the DC operating point. So this is equal to the slope. So the slope of the base current versus the base to emitter voltage in this region is actually important as far as the AC current and the AC voltage of this transistor is actually concerned. Okay, because the slope of this IB versus VBE curve in this region basically dictates what should be the small increase in base current delta IB due to the small increase in base to emitter voltage, and this small increase in the base to emitter voltage is due to this AC voltage source. Okay, so this delta IB divided by delta VBE is basically equal to the slope of the IV curve or IB versus VBE curve at the DC operating point, which is basically this point. Okay, so this is equal to delta VBE at VBE equal to VBEQ. So VBEQ basically means the base to emitter voltage at the Q point. Okay, so Q point is basically the DC operating point. So the base to emitter voltage at the DC operating point. Okay, so we must differentiate this expression over here to get del IB del VBE. This is equal to ISB divided by VT exponential VBE VBEQ actually, because we have found this at VBE equal to VBEQ divided by VT. So this is equal to IBEQ. So the base to emitter current at the Q point or the DC value of the base to emitter current divided by VT. Now this quantity basically has the unit of conductance Okay, so this is known as the small signal or AC conductance. Okay, so this basically has the unit of conductance, and this is known as the small signal or AC conductance. Okay, or the small signal base conductance. So small signal base conductance. Okay, the small signal base conductance basically relates the small increase in the base current due to the small increase in base to emitter voltage at the DC operating point or at the Q point. Okay, so likewise the inverse of this, which is basically uh, del VBE del IB is equal to del IB del VBE inverse. So this is again at VBEQ VBEQ. This is equal to VT divided by IBEQ. Okay, and this is generally denoted by this letter R pi, where this R pi is known as small signal base resistance. Okay, so we can actually write as this small increase in VBE, which is delta VBE divided by delta IB, the small increase in base current, equal to R pi. Okay, now note that we discussed earlier that this small increase in VBE is due to the AC applied voltage. Okay, so this implies that VBE, which is the AC component of the base voltage, divided by IB, which is again the AC component of the base current, is equal to R pi. Note that when we denote this AC components, we basically write it in small case and we write this letters in italics. So when we write in small case and in italics, this basically means that we are writing the AC components. Okay, so basically the AC component of VBE divided by the AC component of IB is equal to R pi. Now note that this R pi basically depends on the DC biasing point. So if you remember, I told you before that to find out the parameters of the small signal or AC model, we actually need to find the DC values of the base current, okay, or the DC values of the emitter current. So this is exactly the reason why that this is the AC or the small signal parameter, and to find out this AC or small signal parameter, we are using the DC values of the base current or the value of the base current at the operating point or the quiescent point. That is why when we want to find out the parameters of the small signal or the AC model, we have to find out the DC values of the base current or the DC values of the collector current first. Okay, so to find out this parameter R pi, which is a small signal model, we have to first find out the DC value of the base current. Okay, so a DC analysis has to be done before we actually move to AC analysis. Okay, so this is our first parameter of this AC model. So this is a parameter of the AC model. Now let us see that how we can actually simplify our equivalent small signal or AC model, or how to draw the small signal or AC model. Let us only consider the base to emitter junction. So in the base to emitter junction, this voltage VCC was basically applied to the base through this resistor RB. Sorry, so let me actually draw the entire circuit here. This was our entire circuit which we have actually drawn earlier, and if we actually want to draw only the base to emitter junction. So this is what the base to emitter junction actually looks like. So we have this voltage source VCC over here, then there is this resistor RB that goes into the base. We are not drawing the collector here, we are just drawing the base to emitter junction and the resistors that are connected to it. This RS is the source resistance, and then we have this capacitor Ci. So RS is the source resistance, and we have this voltage source VAC here, and then this is grounded. Okay, so I am not drawing the collector here. So now we have seen that the parameter R pi basically connects the small increase in base current to the small increase in the base voltage. Okay, so as far as the AC signal is concerned, this base to emitter junction is basically a resistance R pi. So this is the small signal base resistance. Now what to do with this voltage source VCC? Now note that VCC is basically a DC voltage source, and a DC voltage source cannot actually create an AC current. Okay, an AC current cannot originate from the DC voltage source. Okay, so since this DC voltage source cannot give rise to AC current, okay, this voltage source, DC voltage source VCC, is as good as a ground to the AC. Okay, because the function of a voltage source is actually to create current. A voltage source basically induces a current flow through the circuit. Okay, now DC voltage source cannot induce an AC current flow through the circuit. DC voltage source cannot create an AC current flow through the circuit. Okay, so the function of a voltage source is to induce a current flow through the circuit, and since a DC voltage source cannot induce an AC current flow through the circuit, as far as the AC model is concerned, the DC voltage source is actually or can be actually taken as a ground for AC. Okay, so this DC voltage source in the small signal AC model is actually grounded. Okay, so my base to emitter junction basically now becomes this resistor RS, which is the source resistor. Now this capacitor, we would assume that this capacitor is actually appropriate such that the capacitor can be assumed to be a short circuit at the AC frequency. So this capacitor Ci basically acts as a short circuit for the AC current. So we would not put this capacitor here, and then between this point and the ground, there are two resistors. One is this base to emitter small signal resistor R pi, and another is this resistor RB over here. Okay, so we will basically put these two resistors between this point and the ground. One is this RB over here, and another is this R pi. Okay, so this is the equivalent model, AC model of the base to emitter side basically. Okay, and this thing is basically modeling the base to emitter resistance. Okay, so let me write it here that this resistance basically models the base to emitter junction. Now when we are talking about the common emitter configuration, we have basically three terminals. One is the base terminal, the collector terminal, and the emitter terminal. And as we said earlier, that in the common emitter configuration, the input current is the base current and the output current is the collector current. So here we have modeled the base to emitter junction by this base resistor, small signal base resistor. But how to model the collector junction? So note that the collector junction or the current flowing into the collector junction is basically dependent on the base current. Okay, so as far as the transistor is concerned, we have three terminals here. The collector, here is this emitter, and here is this base. And base to emitter junction, we have already seen that this is modeled by the small signal base resistance. So we have 3 points here. This is the base B, this is the collector, this is the emitter. Okay, the base to emitter junction is basically modeled by this resistor R pi. Note that this is only the model that is valid for small signal or AC signals. Okay, AC signals which have small amplitudes actually. Okay, so this model is only valid when the amplitude of the AC signal is small. Okay, so R pi. Now this collector to emitter junction is basically modeled by a dependent current source. Okay, so this dependent current source is equal to beta times IB, and the voltage drop across this resistance R pi is basically V pi. V pi is basically equivalent to the small signal base to emitter voltage drop or the base to emitter AC voltage drop. Okay, so V pi is basically equal to VBE. Okay, and through this resistor R pi, this base current basically flows, the AC component of the base current, because we are dealing with the AC components basically, or the small signal models or the AC models basically. Here this collector current flows, and through this collector junction, this collector current IC equal to beta IB flows. Okay, now we can actually modify this equation over here. So IC is equal to beta times IB, and IB is equal to V pi divided by R pi. So this voltage, the AC component of the voltage at the base to emitter junction is basically V pi. So V pi divided by R pi is basically equal to the base current. This is actually equivalent to saying that this part is basically equal to delta VBE divided by R pi. Okay, the small increase in the base to emitter voltage due to the AC signal. Okay, anyway, so it's actually a convention to write it as V pi divided by R pi. Okay, now this beta by R pi is basically written as GM. So beta divided by R pi into V pi. So this is basically written as GM into V pi. Okay, so this is equal to GM into V pi. Okay, this GM is basically known as the small signal transconductance. Why this is known as transconductance is basically because V pi is basically the small increase in the base to emitter voltage due to the AC signal, but here we have the collector current. Okay, so it appears that this base to emitter voltage or the AC component of the base to emitter voltage is actually giving rise to an increase in collector current, or giving rise to the AC component of the collector current through this parameter GM. Okay, so the base to emitter voltage is actually transforming to the collector conductance through this parameter GM. So that is why this parameter is basically known as transconductance, in the sense that the conductance is transforming or transferring from the base to emitter junction to the collector point. Okay, so in that sense, this is known as the small signal transconductance. So this is basically the small signal model of the NPN transistor. Now earlier we just showed how this base to emitter junction would look. So let me rewrite this. Okay, so this R pi basically models our base to emitter junction, that's just as I said. So let me delete this here. This is our base point. So we should also have a collector point and an emitter point over here. So just as I said that this collector is basically modeled by this dependent current source IC equal to Gm V pi, where V pi is basically this voltage drop across this resistance R pi. Okay. Now, so this current source, this dependent current source basically models the collector to emitter junction. So this is the emitter point E, and this emitter point is basically grounded. Now what about this resistor and this voltage source VCC? Now just as I stated before that this DC source VCC cannot actually create an AC current. So the function of a voltage source is actually to induce an AC current. Since this voltage source VCC cannot induce an AC current through the circuit, this voltage source VCC can be assumed to be AC ground. Okay, so this is the collector point, and this is the collector point here, and this, as I said, that this can be assumed to be the AC ground. So our AC ground is here, and between the AC ground and the collector point, this resistor RC is actually attached. So between the collector and this AC ground, we would attach this resistor RC. Okay, so this is the equivalent AC model for this entire transistor circuit. Okay, so I hope it is not too much difficult to understand. So this small signal AC parameters here are basically R pi, which is the small signal base resistance, and another small signal parameter is basically Gm, which is basically the small signal transconductance. Okay, so these are the two small signal parameters here. Now there is actually a third small signal parameter which is known as R0, which is the small signal output conductance of the transistor, but we will actually learn about that parameter later. So right now let us quickly see how actually to find out or how to relate this small increase in the base current through this model. Okay, so we see that we also know that we take the output voltage from here through a capacitor. So this is our output AC voltage V0. So the AC voltage appears at the collector terminal. So this is our AC voltage V0. Okay, now how do we find what is V0? Okay, so let us just quickly solve this problem here. So what is V pi? What is the voltage drop across this resistor R pi? From this model, V pi can simply be written as V pi equals to RB parallel to R pi divided by RB parallel to R pi plus RS into VAC. This is not difficult to write. We have these two resistors RB and R pi in parallel, and this resistor RS is basically in series combination with the parallel combination of RB and R5. Okay, so this formula is not difficult to write. Now the collector current IC is basically dependent on this V pi through this relation IC equals to GM V pi. So we have found the small increase in the collector current or the AC component of the collector current. Okay, and GM as before is equal to beta divided by R pi. So this is basically equal to beta divided by R pi into V pi, which is basically equal to beta divided by, okay, let us not write this. Now the output voltage V0, how does the output voltage appear? So this current IC, the AC component of the collector current, basically flows through this resistor RC over here. So the output voltage V0 is basically minus IC into RC, because the AC current is flowing from this AC ground through this resistor RC. So V0 is basically minus IC into RC. Okay, so minus IC into RC is basically we just put these formulas over here, this formula and also this formula. So IC is basically minus beta divided by R pi into V pi, and V pi is basically RB parallel to R pi divided by RB parallel to R pi plus RS into VAC. Okay, so therefore we have got the relation between V0 and VAC, and the ratio of the output voltage to this input voltage is known as the gain of the transistor. So the gain A is basically equal to V0 divided by the input voltage. So A is the gain of the transistor, which is V0 divided by VAC, which is equal to minus beta divided by R pi into RB parallel to R pi divided by RB parallel to R pi plus RS. Okay, so very quickly we have actually found out the gain of this transistor configuration from the small signal equivalent model. Okay, although I have done it in very short in this portion, in a very short space, this is actually important. So do not just skip it, do not just think that this is unimportant because it is done in a very short space and skip it. Just try to analyze this yourself, try to do it yourself, that from this small signal AC model, how I have found out the gain of the transistor. Remember that when we are talking about gain, just as I told that when we are interested in amplification, we are basically interested in the amplification of the AC voltage. We are not interested in amplification of DC voltage. We are interested in the amplification of our AC signal, because the signal basically contains information. Okay, so the gain here is basically the ratio of the AC component of the output voltage V0 divided by the AC component of the input voltage. Okay, so V0 divided by VAC. Okay, and we actually discussed this many times earlier, that the gain of a transistor is negative, or the output voltage, output signal, or the AC component of the output voltage is basically 180-degree phase shifted with respect to the input signal. So here also we basically see that there is a minus sign over here, which means that the output signal or the AC component of the output voltage is basically 180-degree phase shifted with respect to the AC component of the input voltage. Okay, let us do up to here today. Thank you everyone.